Welcome to this third lecture devoted to concentration of measure. Today we shall go on the chapter devoted to bounding the variance. And more precisely, what we shall do today is to build some Poincaré type inequalities. What do I mean by Poincaré type inequality? I mean that here we shall consider the case where the variables belong to Rn and where it is possible to introduce some smoothness assumptions because we are in a space where it makes sense to consider smoothness assumptions. So we start from a French-Stein's inequality, and we try to bound the variance by using a quantity which takes into account the smoothness of the function f. And the easiest way to take into account the smoothness of the function f is to look something which looks like a Sobolev norm or something like that. And so we are first assuming that f is continuously differentiable, and we denote as usual, and we consider as usual the gradient of the function f that we denote by this here, okay? And so the theorem that we shall prove right now is the following. If the vector of coordinates x1, xn takes in its values in 0, 1 to the power n, that is, if the variables are between 0 and 1, and if you assume that the function f is separately convex, so you all know what convex means. Separately convex, it's a slightly weaker condition which says that the function is convex with respect to all its coordinates, okay? But not necessarily convex with all the coordinates at the same time. So this is the first condition. And the second condition we are looking at is simply that the variables are standard Gaussian variables. Okay, if one of these two conditions is fulfilled, then if f is continuously differentiable, you are able to bound the variance by the expectation of the square of the Euclidean norm of the gradient. So a simple comment about that, as soon as you have such a bound, if you assume f to be L Lipschitz, this means that the variance will be less than L squared, because for a smooth function, to be L Lipschitz means that the L infinite norm, it means that the norm of the gradient of f will be less than the constant L for all the values that you consider, for all the vectors x. So this means that you get this immediately because L is the soup of the norm of the gradient of the function. But of course, as soon as you have that for all smooth functions, you can relax the smoothness assumption and you can just keep the L Lipschitz condition, and it's enough because you can use an approximation argument to approximate a Lipschitz function by smooth Lipschitz function. So this means that this inequality holds true under the two conditions above, that is, either the variables lie between 0 and 1, or they are standard Gaussian variables, okay? And independent, yes, of course. So it's important to understand that this statement is in Rn, but in fact, Efronstein's inequality tells us that it is enough to prove it in dimension 1. Because as soon as you get this result in dimension 1, you can apply it to all the partial functions, which to t here, to t, you associate the function f at variables x1, x minus 1, and you move only this coordinate here, the number I. And if you do that, you get an inequality that you can sum up all along the coordinates. And since the norm square of the gradient is defined as an additive formula from the square of the partial derivatives, then Efronstein's inequality tells you that if the result is true in dimension 1, it is true in dimension n. So it is enough to prove the result in dimension 1 for all smooth functions. So let's see how it works under assumption 1, because the proof is really straightforward. It's very simple. So we use first the continuity of the function to ensure that the function on 0, 1 achieves a minimum at some point c. And then we use convexity to ensure that the difference between f at capital X minus f at point C is less than x minus c times f prime at capital X. And of course, it is non-negative because c is the minimum. And therefore, since x minus c is between is less than 1 in absolute value, then you get that the variance of the function f of x is less than the expectation of f of x minus a constant.
Yeah, monsieur, pourquoi x moins c moins inférieur ou égal à 1 la valeur absolue de y?
Parce que x et c sont dans l'intervalle 0,1. D'accord? Donc leur différence est entre moins 1 et 1. Et donc en valeur absolue, c'est plus petit que 1. OK?
OK, OK. C est une constante ou non?
C est une constante, c'est un point où f atteint son minimum. So the variance is less than the expectation of f of x minus f of c squared. And so it is less than the expectation of f prime of x squared, just using the inequality above. Okay? And this is it. It is finished. You have proved the result under assumption 1. So as you see, it's very simple. It uses directly boundedness assumptions combined to convexity. So the proof under assumption 2 requires to work a little more. And as you will see, it relies on the combination of an argument, which is just use the central limit theorem, and a clever use of Efronstein's inequality. That is, we shall use Efronstein's inequality again. Okay? So let's see that. So let's see the proof of Poincaré inequality in the Gaussian case. So you have a variable x, which is a standard normal, and you want to show that the variance of f of x is less than the expectation of f prime square of x. So how to do that? So first, you again use an approximation argument to say that it is enough to prove the result if f for all f which are infinitely differentiable but with compact support. And then you consider some random signs, epsilon 1, epsilon capital N, which are independent and identically distributed. And the probability that epsilon 1 is equal to 1 is equal to the probability of epsilon 1 equal to minus 1 is equal to 1/2. And you look at the sum, S capital M, of these variables normalized by square root of n. So it's a CLT normalization. So when you normalize like that, it goes in distribution to a standard normal. So since we have a compactly supported function f, and the same for the derivative f prime, you know that the variance of f of Sn will go to the variance of f of x, and the expectation of f prime square Sn will converge to the expectation of f prime square of x as n goes to infinity. So now we shall use the Reverse inequality
Hi, excuse me, do you hear me?
Yes.
I'm not really familiar with the different types of convergence. Is it trivial to prove that convergence in distribution implies the following two convergences of the variance and the expectation above?
Okay, so it's no, it's not. I would not say that it is trivial, but if you know the definition of the convergence in distributions formulated in terms of the convergence of continuous and bounded function of variables,
right? Okay.
Then it is trivial. Okay. You
okay,
go back
thanks.
to the definition. Okay.
Right. Thanks.
Yes, we use Exponential inequality to bound the variance of f of Sn. And so, as we have seen, Exponential inequality merely says that it is enough to compute variances in one coordinate. Okay, so we have to make this very simple computation just on a pair of signs, because we shall use the symmetrization trick that we have seen last time. So we consider two random signs, epsilon prime being a copy of epsilon, and which is independent of epsilon. And in this case, when you look at a function of epsilon minus a function of epsilon prime, the difference between the two in absolute value is just equal to j at point 1 minus j at point minus 1 times some variable y, which is simply a Bernoulli variable with parameter 1/2. Because when you look at this, either epsilon and epsilon prime disagree, or they do not disagree, and these two events have probability 1/2. Okay. And therefore, when you look at the expectation of j of epsilon minus j of epsilon prime square, then this is equal to 1/2 of j minus j of 1 minus j of minus 1 square. And this 1/2 here comes from the expectation of y square, which is equal to the expectation of y. So if we apply Einstein's inequality, what you get is that the variance of f of Sn is less than 1/4 times the sum of the expectation of what? Expectation of f of Sn plus 1 minus epsilon I over square root of n minus f of Sn minus 1 plus epsilon I over square root of n. And this is squared. Okay? So it looks complicated, but it is simple. You just freeze here the variable, but the number I, and at the I place, you have to put +1. So you subtract epsilon I to Sn, and you put 1. And here you have to put -1. So you do the same, but with -1. Okay? And the 1/4 is just 1/2 times 1/2. 1/2 coming from here, and 1/2 coming from Einstein's inequality, because you use it on with the symmetrized version of the bound of the variance. So now you use Taylor formula. If you use Taylor formula, you can ensure that f at point Sn plus 1 minus epsilon I over square root of n minus f of Sn at point minus 1 plus epsilon I over square root of n minus 2 over square root of n, because the difference between 1 over square root of n and minus 1 over square root of n is equal to 2 over square root of n times f prime at Sn. And this has to be less than 2 times the sup of the derivative, or the second derivative, excuse me, over capital N, which is 1 over square root of n squared. So this is Taylor formula. And afterwards, you take the square of the quantities that you have to bound, that is the difference between f at this point and f at the other point, which is minus 1 plus epsilon I over square root of n. You take the square. So we had the absolute values, we take the square. And of course, this is less than the sum of two squares, the square of this guy here and of this guy here. That is 4 over n f expectation. I take the expectation also. Expectation of f prime square of s capital N plus 4 over n square, the square of the other guy, and a cross product, which is 8 over n to the power 3/2 f prime infinite, because you just bound f prime by its sup here, n times f second infinite norm. And so at the end of the day, you get a bound on the variance of f of s capital N, which is simply less than the expectation of f prime square of s capital N. Because of course, when you look at the bound on the variance, Efronstein's inequality tells you that it is less than the sum of these terms here. But these terms are all bounded by the same quantity, so you get n times the quantity which is here. So, of course, you have the 1/4 which comes from Efronstein's inequality and multiplied by n, because you have a bound on each individual term. So you have to multiply by n over 4. So this gives you exactly this term, plus this term here multiplied by n over 4, that is 1 over n, f second infinite square, and plus this guy multiplied by n over 4, that is 2 over square root of n, the infinite norm of f prime times the infinite norm of f second. So as n goes to infinity, now you get that the variance.
Pourquoi vous multipliez n sur 4? n sur 4 non ou n sur 4? Pourquoi tu multiplies n sur 4?
J'ai compris. Donc on revient à Efronstein. Efronstein.
Oui, c'est 1 sur 4.
Il y a 1 sur 4.
Oui.
Et il y a une somme. Et chaque terme ici dans la somme est majoré par la même quantité. Donc, c'est n sur 4.
OK, OK.
So, as n goes to infinity now, you see that this guy goes to this one here. And on the upper bound here, you get that you simply get the expectation of f prime square of x, and there's two terms here, tends to 0. So you get the required inequality. And this is the end of the proof. Okay. So now our purpose is to go to exponential inequalities And as a transition, I would like to show you that it is possible to prove Efronstein's inequality without using an orthogonality argument, okay? Because you remember that you have made an orthogonal expansion based on a martingale argument in order to prove Efronstein's inequality. So this is a nice proof, but which uses, in some sense, a trick which is fully adapted to the square, but it is no longer adapted to something else than the square. So we have to introduce another way of proving Efronstein's inequality if we want to generalize it on something else. And what is this something else? So we have to think about it a little bit. If you want to go from the square to something, it will no longer be the log of the moment generatory function directly. This quantity will not be the right subadditive quantity to look at. This does not work as easy as that. The square is a special case because the dual, in the sense of convex function of the square, is the square. So we have to think about it a little bit differently. You have to have in mind that it is not the exponential which will play a role, because when you look at the moment generating function, you look at exponential, but it will rather be the dual of the exponential. And the dual of the exponential is the function x log x. And this is this function which will play a very important role for what follows. So this means, in other words, that we have to interpret the variance slightly differently than what we have done right now. So the right interpretation is to look at the variance as a phi entropy. So what is a phi entropy? This is very simple to define. If you consider some convex function on some closed interval I,
Monsieur, pourriez-vous montrer aussi the variance as what? An operator on the space of square interval
yes.
To what? Can you show me the last? Can you show me? Thank you. Can you show me the last slide? The last slide, s'il vous plaît. The last slide, s'il vous plaît. Yes.
This one?
Yes.
Okay. So we shall look at the variance as a functional on the space of square integrable variables. Okay?
Okay.
And we shall interpret it as a phi entropy quantity. And I want now to define what is a phi entropy.
Okay.
Okay? So the phi entropy is what? You consider some convex function on some closed interval I, and you define the phi entropy of an integrable random variable y as the expectation of phi of y minus phi of the expectation of y. Okay. So notice that it is always a well-defined quantity, because the expectation of y is well-defined, the variable y is integrable. And when you look at a convex function of y, the only way for this convex function of y not to be nice is not to be nice from above, not from below. In other words, the positive part of the variable phi of y can be with expectation equal to plus infinity, but not the negative part. The negative part is always with expectation, which is finite. And so it is always meaningful to consider the expectation of phi of y, because you can merely define it as the difference between the expectation of the positive part and the expectation of the negative part. Okay? So it has always made sense. And the Phi entropy is finite if and only if the positive part of the variable has a finite expectation, that is, the function phi of y is integrable. Okay? So this is a thing that you have to notice. And the second thing, of course, is that the variance is indeed a Phi entropy when you consider the case where phi of x is equal to x squared and the interval I is equal to R. And the last comment is that the other interesting example that we shall use during the second half of the lecture is the example where the function phi is equal to x log x if x is non-negative and defined as 0 when you consider the point 0. And of course, it is a continuous function on 0 plus infinity. And it is convex. And we shall prove a subadditive inequality that will generalize F1 inequality in this case. This is exactly the thing that we shall do in a moment after the coffee break. But before the coffee break, I would like to show you that it is possible to prove F1 inequality just using the property of the variance seen as a functional on the class of square integrable variable. And as a functional on the class of square integrable variables, this functional is itself convex in a strong sense, that is, you have a duality formula. So what do I mean by a duality formula? You can express the variance as the soup of a linear functional of y minus some constant. So it's a soup of affine quantities with respect to y. So this is a duality formula. And now, what I'd like to show you first is that it is a very simple formula to prove. It just comes from the fact that the variance of the difference between y and t is simply expressed as the sum of the variances minus 2 times the covariance. And since this variance, of course, is non-negative, this implies that the variance of y is larger than minus variance of t plus 2 times the covariance. And you have an equality when y is equal to t. So this proves that this identity here is true. So this is the duality formula. And now we shall see in a moment that when you use this duality formula on the conditional variance, so you use it conditionally to x bracket I. So remember that x bracket I is the vector with coordinates which are all the xj but xi, you remove xi. Then if you use it conditionally to x bracket I, you are able to prove that the variance of the conditional of expectation of z conditionally to x1 xi, remember that it means that it is conditional to x1 xi, then it is less than the conditional expectation times the variance, conditional variance of z. So here, listen to the music. You are commuting an expectation with an operator, which is a variance, okay? You commute an expectation and a variance, and you see that it can only increase the quantity. So this exactly looks as Jensen's inequality, apart from the fact that it is a strong version because you are commuting an operator with an expectation. Okay, but it is the same music. So let's see that using just this lemma here that we shall prove afterwards, then we can prove Frenchley's inequality without orthogonality. Let's see how to do that. We simply write z square minus expectation of z square as a telescopic formula involving the conditional expectations. But it's an expansion, not an orthogonal expansion. It's an expansion, telescopic formula. And we take expectation on each side. So if you do that, if we do that, we just, of course, recover the variance on the left-hand side. And on the right-hand side, we see these quantities appear here. But of course, you have to remember that because of independence, when you look at a expectation I combined with expectation bracket I, this is equal to expectation I minus 1. This is something that you have seen. And the same if you commute in the other order. Okay? And so if you interpret this expectation I minus 1 as the expectation bracket I of expectation conditional into x1 xi, if you do that, the formula above can be interpreted as follows. You have just an identity which says that the variance is equal to the sum of the expectation of variance bracket I of expectation of z conditionally to x1 xi. So it's in a sense, the difference between this formula and Efrenstein is that you have this quantity here, which appears, but which makes the formula becomes an actual formula that is an equality. And now you see that in order to get Frenchley's inequality, it's very simple. It's just commuting this guy with this one. You commute these two quantities. And then, of course, this one will disappear with the expectation, and you get Efrenstein. Okay? So you use the lemma in order to commute variance and expectation, and then you get Efrenstein. So now I just want to, before the coffee break, to show you how to prove
this lemma implies what? Implies what? Can you show me? Could
the lemma implies, this is the lemma, in fact. You look at the lemma allows you to commute, excuse me. The lemma allows you to put this guide outside the variance. And when you combine expectation with conditional expectation, it disappears. Okay? So it gives you this.
Je ne peux pas comprendre.
The lemma, let's see it again, tells you that you can commute this expectation with the variance. And when you do that, you increase the quantity. Okay?
Mm.
When you apply it now, here in this situation, you commute the expectation with the variance, but if you do that, this expectation will be destroyed by this one. When you take the expectation of the conditional expectation, it's just taking expectation. Okay? And so you get this.
Okay.
So let's see the proof. Let's see the proof of the lemma now. So to prove the lemma, it's a simple computation on the conditional expectations, okay? We have to check first the following formula. That I denote by star, and which says that expectation, the conditional expectation AI of the covariance, the conditional covariance of AI Z and Z is equal to the variance bracket I of AI expectation IZ. So do not be surprised not to see a conditional expectation here. It's just because this quantity is x1, xi measurable. Okay? So to see this, let's just check this formula here. You compute the expectation of the covariance. And you say that you notice that the covariance can be expressed as the conditional expectation of Z times the variable here minus its conditional expectation. And now you use the fact that A bracket I expectation I is equal to expectation conditionally to x1, x minus 1. Okay, use that. And so if you do that, this leads to a computation for the conditional expectation of the covariance above, which is equal to expectation I minus 1, just because you take this expectation here combined with this one. And this is times Z times expectation, conditional expectation I minus expectation I minus 1, just because this guy gives this one. And that's all. Okay? And you make a similar computation. I do not make it explicitly because I leave you as an exercise. It is exactly the same kind of computation. And you compute similarly this guy, excuse me. Like that. You compute it explicitly using the same kind of argument as before, and you get exactly the same formula. That is A minus 1 Z minus 1 Z. Okay, so this shows that the formula star is true. And now the proof is very simple.
C'est étoile, c'est quoi étoile?
Étoile, c'est cette formule ici.
Okay. Okay, merci.
This is this formula. And now we use the duality formula. We use it conditionally to xi. And so we know that the variance, the conditional variance, is always larger than 2 times the covariance TZ minus variance of T for all T. And you choose T equal the conditional expectation of Z conditionally to x1, xi. And if you do so, you get that the variance, the conditional variance, is larger than 2 times the covariance of AIZ Z minus the variance of AIZ and if you use the formula star, the star formula, tells you that the expectation I this time of the variance will be larger than the variance of AIZ, because when you take the expectation, the conditional expectation, you see that when you make appear is 2 times this guy minus this guy, so it gives you only this guy. The formula here, go back to this formula, you see that when you take the conditional expectation, you make the variance appear. So if you go back here, when you take the conditional expectation, this term here will merely becomes, when you take the expectation on it, it becomes 2 times this one. And so this gives you 2 times this one minus this one. So it gives you 1 times the variance. And the proof is over. Okay, so it's some kind of a strange exercise because in some sense, it gives you a more complicated proof of the result, but this more complicated proof can be generalized. This is the idea. And this is what we shall do after the coffee break by looking at information inequalities. So now I stop the record and we make a coffee break. Let us begin the 4th chapter devoted to information inequalities. So as we shall see, there are several notions of entropy that exist in the literature. Historically speaking, the first one has been introduced by Shannon. So information theory is a world by itself. I do not pretend to give you an overview of what can be done in information theory. My ambition here is just to give you some statements that will be useful for us in what follows. So nevertheless, let us begin with the simplest notion of entropy and of information, which is the notion introduced by Shannon for discrete variables. So what is Shannon entropy? It's very simple to define. You take some discrete random variable. You just consider the weight, the quantity P of x, which is a probability that x is equal to small x. And Shannon entropy is defined as a non-negative quantity, in fact, because it is defined as the expectation of minus the log of a quantity which is less than 1. So it is expectation of a non-negative quantity. And you can express it explicitly as minus the sum of P of x times the log of P of x. So it's a quantity that we denote by capital H of the variable, but in fact, it depends on the variable only through its probability distribution, obviously. So this is Shannon entropy, which plays a very important role in coding theory and in discrete signal processing. And if we want to generalize this concept of entropy from the discrete case to an abstract probability framework, then the key notion to be considered is relative entropy. So what is relative entropy? It's also a simple thing to consider. You take another probability on the discrete space X, and you take a probability Q, which is such that the P is absolutely continuous with respect to Q. That is, when Q is equal to 0, P has to be equal to 0. And if you take the convention that 0 over 0 is equal to 0, the relative entropy is simply defined as the sum of P of X times the log of P of X over Q of X. And this is a non-negative quantity just because you use the fact that log U is less than U minus 1. And you write the sum of the P of X log Q over P of X simply by using this inequality on the log. You rewrite things in order to make this ratio appear here. And of course, you see that doing this, you simply make 0 appear because you have appearing simply the sum of the P of X, which is equal to 1, and the sum of the Q of X, which is equal to 1. So you realize that it is equal to 0. And so this means that the relative entropy is non-negative. So when X is a finite set, there is a relationship which is very easy to make between Shannon entropy and relative entropy. Since if you take Q to be the uniform distribution, then the relative entropy of P relatively to the uniform distribution is merely the log of the cardinality of the set minus Shannon entropy. So this tells you, since the relative entropy is non-negative, this tells you that the Shannon entropy is non-negative, and it is also less than the log of the cardinality. And this is here an equality if and only if P is uniform. Okay? So these are very simple things about Shannon entropy and relative entropy. So now we turn to the entropy of a random variable. So I consider again the definition of Phi entropy with the function phi being the function x log x. So we look at this notion of entropy of a random variable again. And it is the same statement as before, but in the particular case where phi of x is equal to x log x. Excuse me. Whoops. And of course, we shall write entropy of the variable with respect to the probability distribution, just to keep in mind that there is an underlying probability distribution on the space, but when there will be no ambiguity, I shall simply remove the index P here when there is no ambiguity, okay? So now when you look at a probability distribution...
Tu parles trop vite. Je n'ai pas encore fini de noter la définition, merci.
Okay, so it's the same as before. This is the reason why I have been quick. It's just because it is the same definition as before. I have already introduced the notion of Phi entropy, and I just recall the definition in the special case where the function phi is equal to x log x, but it's the same definition, of course. So now, if you consider a probability distribution which is absolutely continuous with respect to P, the general way of defining the relative entropy is just to consider the entropy of the Rodin derivative of Q with respect to P. Okay? And doing this, you recover exactly the definition that we had in the discrete case, just because in the discrete case, when you look at the Rodin derivative, it's just the ratio between the weights, okay? And so you recover a formula which is exactly the same as the one that we have given before in the discrete case. Does everybody know what is a Rodin-Nikodym derivative? Yes? That's okay? Okay.
P, non, P oméga, je ne peux pas comprendre les symboles, merci. Je ne peux pas comprendre les symboles.
Here?
Oui. Q oméga, c'est quoi?
Omega is a countable set, okay, here. Omega is the underlying probability space. In the case where it is discrete, that is in the case where it is at most countable, okay, I may define the probability just by looking at the probability of the elements of omega, okay?
Okay.
And so in this case, the Rodin-Nikodym derivative is merely the ratio between the weights here, okay? That's very simple. That's a basic probability theory in the discrete case. So now the heart of the matter is that for this notion of entropy, we are able to prove a duality formula which will play the same role as the duality formula that we have seen before for the variance. But now the set of variables on which you have to see the entropy acting is no longer the set of square integrable variable as for the variance, but it is the set of non-negative and integrable variable. It is the right set to be considered when you look at entropy. It is acting on this set of variables. And then what does the duality formula say? It says that the entropy can be computed as a soup. It's a soup of the expectation of y times log t, and log t, nt, excuse me, has to be taken as a non-negative integrable variable, such that either the expectation of t is equal to 1 or the expectation of t is less than 1. It is the same. Because as we shall see, this supremum among all these variables is achieved for the variables which are exactly on the border. Okay? So this is the duality formula. And this duality formula has a converse, which says that if t is a random variable such that for all non-negative and integrable variable y with expectation equal to 1, the entropy is larger than the expectation of y times log t, then conversely, it means that the expectation of t is less than 1. Okay? This is the statement. So there is an easy comment, which is simply that you can rephrase a third time, I would say, the supremum which is taken here. You can take the supremum over all the variables, which are non-degenerate, okay, non-equal to 0, of the expectation of y times log t minus the quantity, which makes the variable here with an expectation equal to 1. This is equivalent to writing this as the log of t over expectation of t.
Okay? Je peux pas voir le soup les mots au-dessous de sous le soup. Les mots soup.
Here?
No, alternatively. No. Alternatively.
Alternatively.
Je peux pas voir soup.
If you stop moving your mouse, the toolbox disappears.
Quoi?
If you stop moving your mouse, the toolbox disappears if that's what's bothering you.
Pourriez-vous taper dans le partie de chat? Ok, j'ai vu. Merci.
Okay. So let's go on. Okay, so excuse me, I have to prove the duality formula, and then I shall show you the corollary. So now I see we make the proof. Let's prove the duality formula. So first, let us show that the soup is achieved at the border. So let us show that the soup over the variables which have expectation less than 1 of expectation y times log t is also the soup over the variables which have expectation equal to 1. So this is simple. You simply consider t tilde, which is t over expectation of t. Then if you look at the expectation of y times the log of t tilde, it is just the expectation of y log t minus the expectation of y times the log of the expectation of t. But of course, since the expectation of t is less than 1, this quantity is non-negative. And so this means that when you turn from t to t tilde, you just increase the expectation. Okay, so the expectation of y log t tilde is larger than the expectation of y log t. So you started from a t which has expectation less than 1, and you have constructed a t tilde with expectation equal to 1, and which is such that the expectation of y log t tilde is larger than this guy. So this means that the soup is achieved on the guys which have expectation equal to 1. Okay, so star was true. So that's one point. Okay, so now another simple remark is that when you look at the expectation of y times log t, then it is equal to the entropy of y whenever t is equal to y over expectation of y. So this means that the thing that you have to prove is that entropy is larger than this quantity, and afterwards the soup is achieved because it is achieved for t being equal to this guy. So it remains to prove that entropy of y is larger than expectation of y log t for all t such that the expectation of t is equal to 1. This is what we have to prove. So we introduce a change of probability. We introduce the probability q such that q is equal to t times p. That is, the Rodin derivative of q with respect to p is equal to t. And we compute the entropy of the variable y over t under this new distribution. So of course it is non-negative, and it is equal to the expectation under p of y log of y over t. And this expectation is exactly equal to the entropy of y, computed under p, of course, minus the expectation of y log t. So this tells you that this quantity here is non-negative. And therefore, you derive that the expectation of y log t is always less than the entropy. And this gives you the direct sense of the statement. So now we have to prove the converse. For the converse, there is a small difficulty. You do not know in advance that t is integrable. So you have a conclusion to get about t, but you do not know that t is integrable. So first, assume that t is integrable. So if it is the case, we know, this is the assumption, we know that whatever y with expectation of y equal to 1, y non-negative, we know that the entropy of y is greater than the expectation of y times log t. And we just set, we choose y equal to t over the expectation of t. If you do that, then the entropy of y is merely the expectation of t over expectation of t times the log of t over expectation of t minus 0 because this guy has expectation equal to 1. And so this is equal to 1 over expectation of t times expectation of t log t minus the log of the expectation of t. And so since we know that the entropy of y is larger than the entropy of y log t, which is merely 1 over the expectation of t times the expectation of t log t. The combination with this and this implies that minus the log of the expectation has to be non-negative, and this means that the expectation of t is less than 1. So if t is integrable, we've got that the expectation of t is less than 1, and it's okay. Otherwise, you do exactly the same thing, but with a truncation. You consider t infimum with n and make n goes to infinity. I do not give you the details here because the details are given in the notes, so it's better that you look at it in the notes. The essence of the proof is exactly what I have done. Okay? So now I turn to one corollary of this duality formula. First, I would like to make some comment. In order to prove concentration inequalities, we have to find an idea to encode subgaussianity by using entropy. And we shall see essentially two different ways of doing this. One will be very well adapted to what we shall call the transplantation method, and the other one is adapted to what we shall call the entropy method. So I begin, excuse me, to give you a corollary of the duality formula that we shall use when we shall see the transplantation method to get concentration. But it's a corollary which is interesting by itself, so I prefer to give you it right now, even though we shall use it slightly later on. But let's see that this corollary, which is rather illuminating, this corollary tells you that you can express the log of the moment generating function with as a soup of quantities which involve the relative entropy notion. So it relates, in some sense, the notion of moment generating function and the notion of entropy. Okay? So let's see the proof of the corollary, and afterwards we shall see some applications, simple applications. So the proof of the corollary so we have to prove that psi y of lambda is equal to the sup over the q, absolutely continuous with respect to p, of lambda expectation of y under q minus the relative entropy of q with respect to p. So let's call this quantity rho of lambda. We have to prove that psi is equal to rho. So first prove that psi is larger than rho. For this, we use the direct sense of the duality formula. We just consider t, which is equal to exponential of lambda y minus psi y of lambda in the duality formula. So this gives you that the relative entropy, remember that it is an entropy, the entropy of the Radon-Nikodym derivative. This tells you that it is larger than the expectation of the Radon-Nikodym derivative times the log of this t. This very t that you have defined there. Okay? And so this tells you that the relative entropy is larger than, look at the definition here, you just have the lambda expectation under q of y minus psi y of lambda. Just because when you look at the log of t, you have lambda y which appears, and you have to integrate it against the Radon-Nikodym derivative, which amounts to compute the expectation under q. So this gives you the first term. And the second term, which appears when you look at the log of t, is a constant, which is minus psi of lambda. And so this constant, you integrate it against a density, and you get 1 times the constant. So you get this. And this gives you exactly the thing that you want, because when you have this, this implies that psi y of lambda is always greater than lambda expectation minus the relative entropy. And this is true for all q. And so psi is greater than the sup, and the sup is what we have called rho. So now you have to prove the reverse inequality. So to prove that it is less than rho now, we do exactly the same kind of thing, but this time, instead of subtracting psi, we subtract rho. That is, we choose t equal to expectation of lambda y, but minus rho. So if q is absolutely continuous with respect to p, the entropy of dq over dp. So we have in mind to use the converse. We use the converse of duality formula. So we have to look at what happens when we look at the entropy of any variable with expectation equal to 1. But this is equivalent to look at any distribution which is absolutely continuous with respect to p. This is the same. So we compute this quantity here minus the expectation of log t dq over dp which is of course equal to the relative entropy minus the expectation of y under q plus rho of lambda. This is the same computation as before, but here instead of psi we have rho. And now by definition of rho, which is the soup of minus this quantity here, this guy is non-negative. Just by definition of rho f lambda. And so this means that the entropy of dq over dp is always larger than the expectation of log t dq over dp. And by the converse of duality formula, this implies that the expectation of t has to be less than 1. And expectation of t has to be less than 1. What does it mean? Look at the definition of t. The definition of t is here. If I say that the expectation is less than 1, this tells us that psi has to be less than rho. And the proof is over because we have proved the two inequalities at the same time, that is rho larger than psi and psi larger than rho. So rho is equal to psi. And the duality and the formula is proved. So we can go again to the presentation here. And so we have this corollary which links the log of the moment generating function to entropy. And so this is very powerful because this leads us to a characterization of sub-Gaussian variables. And this characterization is just here. A variable y will be such that the log of the moment generating function is less than lambda square over 2v if and only if this relation holds about the difference between the expectation of the variable under q. So here there is a misprint. It is not y, this is z. And a quantity which is defined in terms of the relative entropy of q with respect to p. And this gives you a very powerful tool. We shall use it to prove concentration by the transportation method, as I mentioned. But right now we can use it to prove to solve an exercise. And this exercise is simply prove Pinscale's inequality. So Pinscale's inequality tells you that the total variation distance between P and Q is less than the square root of the relative entropy over 2. And this is an inequality which is not that easy to prove if you do not use the trick of using the lemma above. In fact, the proof that this inequality holds true with this constant 1/2 is due to Shizar, Emre Shizar. And it's quite an intricate proof, which uses real analysis in a very clever way. And we shall see a very, very easy proof just by using the lemma. So we shall see this in a moment, but first, let us see that the lemma holds true. So the lemma just stated here gives you a characterization of subgaussianity in terms of this inequality here. So let's see that it is true. So it is very simple, in fact. Let's look at this strange statement, which is expectation of Z under Q minus expectation of Z under P is less than the square root of 2V times the relative entropy. And the trick is that this quantity here is equal to the infimum over non-negative values of lambda, positive values of lambda, excuse me, of the relative entropy plus lambda square V over 2 over lambda. This is very easy to check. The infimum is achieved at lambda equal to square root of 2 times the relative entropy over V. So, saying that this is less than this quantity, which is an infimum, is equivalent to say that this guy is less than all these guys here. And of course, I can multiply by lambda. So if I multiply by lambda, this tells me that lambda expectation of Z minus expectation of Z here minus the relative entropy is less than lambda square V over 2. And this has to be true for all lambda positive and for all Q absolutely continuous with respect to P. And so this tells you that the supremum of over Q absolutely continuous with respect to P of lambda expectation of Z minus expectation of Z here minus the relative entropy is less than lambda square V over 2. And this has to be true for all lambda. And now you use the corollary to say that this is equal, this guy here, is equal to the log of the moment generating function of z minus expectation of z. Okay, and this gives you the characterization of sub-Gaussianity that I have mentioned, and I realize that here there is still a misprint. Excuse me. Up. No, not this. This. So this is not y, excuse me. This should be z minus expectation of z here instead of y. There is a misprint. Okay, so this allows you to characterize sub-Gaussian variables in a strange way, but let's see how it is powerful by looking at the consequence for Pinscale inequality. So let's see how to prove Pinscale inequality. This is very, very simple because now you look at the total variation distance, which is defined as the soup over the measurable sets of P of A minus Q of A. And if Q is absolutely continuous with respect to P, excuse me, this is the converse. You may express this soup. You know where this soup is achieved. It is achieved for A plus, let's say, which is the set where dq over dp is larger than 1. This is very easy to see. And so this is equal to q of A plus minus p of A plus. And therefore, if you look at the random variable z, which is equal to the indicator of A plus, this variable is between 0 and 1. And you know from Hoeffding's lemma that the log of the moment generating function is less than lambda square over 8. And therefore, when you use the characterization of sub-Gaussian variables that we have seen before, this means that the expectation of z under q minus expectation of p of z under p has to be less than the square root of 2v times the relative entropy with v equal to 1/4. And therefore, this gives you that q of A plus minus p of A plus is less than the square root of the relative entropy over 2. And this is Pinscale. So this is a very, very nice exercise, very nice and elegant way of proving Pinscale's inequality, starting from this characterization of subgaussianity. So this is an idea that we shall use when we shall study in details the transportation method. But for the moment, we shall focus on the entropy method and focus on our aim of proving an analog of Efronstein's inequality for the entropy instead of the variance, that is a subadditive inequality, just building on the duality formula. So let's do that. So let's consider conditional entropies. So conditional entropies will just be defined as usual entropies, but substituting conditional expectation to ordinary expectation. So the definition is very simple. You look at the definition of entropy, but you replace the expectation by the conditional expectations. Okay, so the conditional expectation, conditional to what? Conditional to x bracket I, where x bracket I is always defined as this guy here. That is all the variables but number I. So if you have this definition in mind now, the statement of the subadditive inequality for entropy is just what you can expect. You consider some non-negative and integrable function of independent variables, and then the entropy of this quantity is less than the sum of the expectation of the conditional entropies. So this is exactly an extension to entropy of the inequality that we had for the variance. For the variance, it was just Efronstein's inequality. And there we have this subadditive inequality for entropy. So as we shall see, it will be possible to extend this to Phi entropy functionals in general, but as we shall also see, it will mean that a special condition of the function phi will have to hold true, because it is not true in general that phi entropy functionals are convex. It is true under some special condition on phi that we shall study in details afterwards. But for the moment, I would just like to show you how to prove this subadditive inequality for entropy. The proof is very simple. This is good news because it is very simple. So the proof of duality formula for entropy, not duality formula, excuse me, of the subadditive inequality. So we start from the definition of entropy. Which is just like that. And we use a telescopic formula again. We write it as the expectation of the sum of y times the log of the conditional expectation ai of y minus the log of the conditional expectation ai minus 1 y. Okay. Recall that this means expectation conditionally to x1 up to xi. And of course, E0 is just ordinary expectation, and En is identity because y is x1 xn measurable. Okay, and again, we use the fact that the expectation bracket I of expectation conditionally to x1 xi of y is equal to the expectation conditionally to x1 up to xi minus 1 of y. So we shall use this. And of course, now we use the duality formula for the conditional entropy. Entropy conditionally to x bracket I. And if you use it conditionally, this means that the conditional entropy of y has to be larger than the expectation, the conditional expectation of y times the log of t minus the log of the expectation bracket I of t. And this has to be true for all t. And now we choose t equal to expectation of...
Monsieur, qu'est-ce que c'est? T appartient à quoi? Qu'est-ce que c'est?
L1 plus the set of non-negative and integrable variables. So we choose t as the conditional expectation of y conditionally to x1 up to xi. And which, if we choose t like that, since expectation bracket I of expectation conditionally to x1 xi is equal to expectation conditionally to I minus 1, this implies that the conditional entropy of y is larger than the expectation bracket I of y, the log of this guy minus the log of this other guy here. Okay, we use this fact that we have already seen. Because of independence, we have this relationship. And then we use it here to compute this quantity when t is defined as a conditional expectation. And so we make this term here appear. And now the proof is almost finished because we just take expectation. And if we take expectation, the expectation of the conditional entropy will be greater than what? Expectation of conditional expectation, this gives you expectation of y log minus log of the same guy as before. And now the proof is over because you just have to combine with star, where star is the original decomposition that we have done here. Here we have decomposed entropy of Y as the expectation of this telescopic sum. And this telescopic sum, we see that each term in this telescopic sum is less than the expectation of the conditional entropy. And this is precisely the thing that we wanted to prove, because we wanted to prove that the entropy is less than the sum of these quantities here. So the proof is over. So you see that the duality formula directly implies the subadditive property for entropy. Now we turn to a very important idea, because in this approach, which builds on the subadditive inequality to go to concentration, we need an argument, an extra argument in some sense, to understand how to encode the sub-Gaussianity of a variable. So we need a new idea here to understand how to really express the sub-Gaussianity of a variable using the entropy of the exponential of lambda z, because all we have in our pocket now is this subadditivity inequality, and we want to use it on the transform of the variable. Of course, we shall not use it on the variable itself. It does not make sense. The variable is not necessarily non-negative, so we shall use it on this exponential transform. But now the issue is how to encode the sub-Gaussianity on the entropy of this exponential of lambda z quantity. So we need an idea. Okay, so let's come back to the situation that we have faced when we have looked at the simplest example of sub-Gaussian variable, that is the example coming from Rodin. Let's go back to Rodin. Rodin tells us that the bounded variable is sub-Gaussian, but it tells us something which is slightly stronger. It tells us that the second derivative of the log of the moment generating function is controlled by a proper value, this value being, remember, the b minus a square over 4. But never mind, it's under control. We have a control on the second derivative. But now look at closely the ratio between the entropy of the exponential of lambda z, which will be the quantity that we can look at, in fact, when we apply the subadditive inequality to the exponential transform of the variable. And look at what happens when I look at the ratio between this quantity and the Laplace transform, that is the moment generating function. When you look at this, then this is simply, simple computation, lambda times psi prime minus psi. Okay, but now if I derive this quantity with respect to lambda, I discover that is nothing else than lambda times psi second. The psi prime disappear. Okay, they destroy themselves when you look at the derivative. And you just have the lambda times psi second. So this means that if you use the stronger conclusion of Rodin's lemma, which is psi second is under control, then if you integrate the preceding inequality, you get that the ratio between the entropy of exponential lambda z and the moment generating function is controlled by lambda square V over 2. Okay, but now the interesting fact is that if you take this and you ask yourself, well, what does it mean for a random variable, this inequality here? The answer is, it means that it is subgaussian. So what we have in our pocket now is that if you take a bounded variable, then this inequality holds. And if this inequality holds for a variable, this means subgaussianity. So we have a way of encoding subgaussianity here. Okay? And this is what is called Erb's argument. So Erb's argument tells us that for any variable which is such that this inequality holds, either for non-negative values of lambda or for all lambda, then this implies that the moment generating function, its log, is controlled by the quantity that we know right now, that is lambda square over 2v, which is merely the log of the moment generating function of a centered Gaussian variable with variance equal to v. Okay? So this means that we have a way to encode subgaussianity just by looking at entropy of exponential of lambda z. This way is given by this Erb's argument. So let's see the proof of Erb's argument. It's not very difficult. It's simple analysis, in fact. So we just define z tilde, which is the variable z minus its expectation. So we center the variable. If we are doing this, the ratio does not change. The ratio between the entropy and the moment generating function does not change at all. It is an homogeneous quantity here. So this means that this quantity is also less than lambda square v over 2. Okay. So now, when you look at 1 over lambda, you divide this by 1 over lambda square, divide by lambda square, excuse me. What you get is 1 over lambda square, expectation of z tilde times exponential of z tilde over expectation of lambda z tilde times lambda. This is the first term of the entropy. And the second term of entropy makes 1 over lambda square and log of expectation of exponential lambda z tilde appear. And this is less than v over 2. But look here, this quantity, look at it carefully. This quantity here, you have this square which disappears with this lambda here. And this shows that this quantity is nothing else than 1 over lambda, the derivative with respect to lambda, of 1 over lambda the log of the moment generating function of Z tilde. And this is less than V over 2. So you just have to integrate this now, taking into account the fact that at 0, this function, as well as its derivative, is equal to 0. Here it's obvious, and here it's true because the variable Z tilde is centered at expectation. And of course, this gives you at the end of the day that the log of the moment generative function of Z tilde is less than lambda square V over 2. And this is what we wanted. So we have this very nice Herbst argument now, which tells us that if this inequality holds true, then the variable is the recentered variable, excuse me, is sub-Gaussian, or at least on one side or on both sides, if you decide to have this relationship for all lambda. Okay, so that's it. We've got our idea. Our idea is use Herbst argument. And this is very important because now you will see that right now that this will lead us to our first strong concentration result, that is a concentration with an exponential inequality. We shall prove it in a moment. And as we shall see later on, with variations around this Herbst argument, we shall be able to prove other concentration inequalities. So this is very, very important, this Herbst argument. So Herbst argument gives us the appropriate way of seeing the sub-Gaussian property when we want the entropy to be involved. That is, we look at this way of encoding sub-Gaussianity. Okay, this encodes a sub-Gaussian random variable.
Excuse me?
Yes.
Could you show Herbst's argument again, not the previous slide, but the one before?
Yes.
Yeah, that one, because what it says is if the ratio is smaller than lambda squared V over 2,
yes,
then it's sub-Gaussian. Is the reciprocal true as well?
No, no, the converse is not necessarily true, but what is interesting is that when we look at the example of which comes from Rodin's lemma of a bounded variable, then in this example, you have a control on the second derivative, which is a stronger result than the control on the moment generative function itself. And so we have indeed this ratio control also. This is what we have seen.
Okay, but then what I don't understand is you say we should encode sub-Gaussianity using this, but as it appears, it doesn't work in all situations when the variable is sub-Gaussian, right?
You're absolutely right.
Okay.
But, it's you are absolutely right. But what I was meaning is that in the use that we shall have afterwards of this argument, the examples that we shall use will in fact obey to the control of this ratio.
Okay, thank you.
Okay, this is exactly what I meant. That is, when you look at the bounded variable, then it's a fact that this control holds true. Okay? So the converse is true in this example. This is what we shall use afterwards. Okay, so let's see now the first exponential concentration inequality that we want to prove. And this concentration inequality is very natural. You consider the situation, the smoothness assumption that we have mentioned when we have studied the control of the variance, that is the bounded differences condition. If the bounded differences condition holds true, we have seen that the variance of Z has to be less than V, where V is defined as the sum of Ci squared over 4. This is what we have seen. And here we have the stronger result that the moment generating function itself is controlled by the one of the corresponding normal variable with variance equal to V. That is, the variable recentered is sub-Gaussian. So this is an equality which is due to McDiarmid. The proof, the original proof, is based on the martingale argument. And here we are revisiting this inequality and provide a proof which is completely based on the subadditivity argument, the subadditivity inequality for entropy. So let's see this proof to finish today's lecture. And as you will see, it is very simple and I think very elegant. So the proof of McDiarmid's inequality . So we use, as announced, the subadditive inequality for entropy applied to the exponential transformation of the variable Z. So we apply it on this. So we have these conditional entropies which appear here. And now we use Hovding's lemma on its strong form. That is, we use the fact that the ratio of the conditional entropies are controlled by lambda square Ci square over 8. Okay, this is exactly the same thing that we have done for controlling the variance. We use the fact that when you move in one coordinate, you simply have to face to a bounded variable. Okay, so you can apply Hovding's lemma, and we have seen a few minutes before that Hovding's lemma, in some sense, has a stronger version, which is expressed in terms of the ratio between the entropy and the moment generating function. So this is this form that we use. And if we plug this into the subadditive inequality, then what we get is that the entropy of exponential of lambda Z is less than lambda square over 8 of the expectation of the sum of the Ci square times the conditional expectation of exponential lambda Z. And now, of course, expectation of a conditional expectation makes expectation. And you discover that the ratio between the entropy and the moment generating function is controlled by lambda square over 2 times v, with v equal the sum of the ci square over 4. And therefore, Erb's arguments implies that the variable is sub-Gaussian with variance factor equal to v, and the proof of McDermott is completed. So you see, this is very, very neat and clever in some sense, because this way of seeing a sub-Gaussian variable is exactly the right one if you want to prove McDermott, because it holds true for a bounded variable by Hovding's lemma, or at least by the strong form of Hovding's lemma in the one hand. And on the other hand, when you have this in your pocket, this implies sub-Gaussianity. Okay? So thank you for your attention, and see you on the next week.